Hey guys, welcome back to another lecture video for Chem 104. In today's video, you guys are going to learn how to name alkanes with substituents. And so this is a very critical video for our organic chemistry section of this course, just because it sets the foundation of the patterns in naming organic compounds for compounds that we'll talk about in the future with functional groups and all of that stuff. And so I really do hope that after working through many or several examples and showing you how to name these alkanes with substituents, you guys can pick up on the pattern and be able to go back and replay some parts of this video and try them out on your own. I'll also post a PowerPoint of this lecture, all of this lecture, actually chapter 11, on Canvas. And so if you guys open up that PowerPoint and scroll to the slide that contains these examples, at the very bottom of that slide, there should be a notes section. So if you enlarge or expand the notes section of my PowerPoint, all of the answers should already be posted. And you can go ahead and use these slides. It's kind of like a worksheet to give you some practice on how to name alkanes with substituents. So let's go ahead and start. The first thing that we need to address is what is a substituent. And so substituent can be used in different fields for different definition, giving it slightly different definitions. So for organic chemistry, a substituent is a substance that's attached to the parent chain of a carbon or organic compound. And so we're going to learn very soon how to identify substituents from parent chains. And so for the main purpose of this course, we're only going to be focusing on two different types of substituents: carbon-based substituents, or alkyl groups, halogen-based substituents, or halo groups. Okay, so let's look at a few examples to understand what an alkyl group or a halo group substituent is. All right, so let's go ahead and look at this image on the left-hand side. So this is the somewhat of the expanded structure. It's kind of like a hybrid between expanded and condensed. And so if you guys look at the structure, the carbon chain that's the longest with the consecutive number of carbons, that is considered your parent chain. And so this carbon is connected to this carbon, which is connected to this carbon, which is connected to this carbon. And so we can go ahead and assume that the carbons that I've highlighted is the carbons of your parent chain. And so that means that these other items that I did not highlight, such as bromine and CH3, they are going to represent our substituent, our attachment. Okay. Now, I didn't circle or box, I apologize, I didn't box the other hydrogens, just because if you guys recall in organic chemistry, we do not include the hydrogens in the skeletal structure. And so if you guys were to draw the skeletal structure of this specific compound, since we have 1, 2, 3, 4, we're going to have a chain that looks like this. And on the first carbon, we're going to have a bromine. And so I'm going to draw a line to represent the attachment of a bromine. And then on the second carbon, I'm just going to draw a line. Now, if you guys recall, this little endpoint of that line represents one carbon, and it's implied that there are 3 hydrogens already attached to it, so it's invisible. Okay, so this would be like the skeletal structure of this compound. And drawing the skeletal structure of this compound actually helps us see what our substituents are. And so once again, these two will act as our substituents. Now, if you were to look at this diagram, or this molecule, we have 1, 2, 3, 4. So these 4 carbons are connected to each other. Now, if you had said, okay, well, what about this carbon on the top? Yeah, they're symmetrical, right? And so whichever carbon you guys highlight in this specific example, that's going to represent the overall carbon chain. And so if you want to translate this in terms of a skeletal structure, since we have a 4-carbon chain, we're going to put 1, 2, 3, 4. And then once again, on the carbon that's on the left-hand side, it has that bromine. So I'm just going to go ahead and draw a line and put bromine. And then on the 3rd carbon, or the second to the last carbon, there's a CH3. So it's sticking up, so I'll go ahead and draw it sticking up. And so the items that are not part of the parent chain, the items that I just circled, is going to be my substituent. Okay. And so looking at this example, this last example, here I have 1, 2, 3, 4 carbons. Now if you highlighted the other carbon, that's okay. These 2 in this scenario is symmetrical, right? They're both on the same carbon. So you can choose either one to represent that 4th carbon for your parent chain. And so since we have a 4-carbon chain, we're going to put 1, 2, 3, 4. And this time, the 2nd carbon from the left, starting from the left, is going to have that bromine, and the next carbon to it is going to have that methyl group, the CH3. In this example, I'm putting this CH3 at the bottom to demonstrate that you can place that methyl group up or down, but it just has to be on the same carbon. So for example, if you drew your skeletal structure in this form, that's also correct. Okay. And so hopefully this exercise shows you how we're going to depict these substituents on our parent chain. Okay. And so you can think of substituents as like the attachments on the parent chain. And we're going to learn how to name them with the parent chain. So we're first going to talk about alkyl groups. And so alkyl groups are a type of substituent. Remember, there are 2 types that we're going to discuss: alkyl groups that are carbon-based and halo groups that are halogen-based. And so alkyl groups are carbon-based substituents. And so these alkyl groups was formed by removing 1 hydrogen from an alkane. Okay? And so since 1 hydrogen was removed from an alkane, we're going to change the ending from an ane to an il, or YL. So this is the reason why we see a YL at the very end of the name, alkyl. So an alkyl is telling the reader that this carbon-based compound is going to be a substituent. Okay. And so this alkyl group can bond to something else. So let's understand this with examples. So typically, methane has only one carbon. And so if you decide to remove one of the hydrogens such that it's unsaturated, you get something that's called methyl. Okay? So that YL is telling you that this carbon-based group is going to be attached to a parent chain. So I'm going to depict that with a squiggly line. And so this guy is being attached to something else. Okay. And so once again, I can put that squiggly line here if I want to depict it in its condensed structure form. Now, if you have ethane, so it's a 2-carbon organic compound, and if you remove one of its hydrogen, then you get still a 2-carbon compound. That's why we keep eth. But since it lost one of its hydrogens so it can act as a substituent, we're going to attach the ending YL. So this is known as ethyl. And so once again, I'm going to put that squiggly line to represent that this organic compound is attached to something else. It's attached to a parent chain. Okay? Okay. Now if we continue this pattern for all alkyl groups, then we get something like methyl, ethyl, propyl, butyl, pentyl, hexyl, heptyl, octyl, nonyl, decyl, where the prefix meth, eth, prop, but, pent, hex, hept, oct, non, and dec still represents the number of carbons that is in that chain of substituent, but the YL ending is letting us know that it's not a parent chain, that it is an attachment to something else. Okay? So what is an example of this? Okay? I understand the pieces that you're giving me, but I don't understand the whole entire picture. So let's go ahead and look at an example. Let's say that we have a 4-carbon compound. And let's say that, and I'm going to put this in a different color, I place 1 carbon, a CH3, on this organic compound that I drew in blue. And so the item that I drew in blue is representing my parent chain. And the item in pink is representing my substituent. And so because I have a CH3 as a substituent, I am going to name that substituent methyl. Okay. So there is that CH3. And I'm going to name this substituent methyl. Okay. What if I have, for example, I'm going to build on to this chain here. Okay. What if I have, a CH2, CH3? Once again, anything in pink is going to be my substituent. Since I have CH2, CH3, I'm going to look at my chart and I'm going to see, that a CH2, CH3 attachment is going to be named ethyl. Now, I've drawn like all the carbons in the substituent, just to clarify it, right? Just to make that connection between this chart and this image. However, when you guys are drawing these organic compounds, these substituents are going to be still represented as a skeletal structure. And so if this is going to be your parent chain, and my pink will be my substituent, I can, for example, just depict the substituent as a line. And that line, since there's only one carbon, it is going to represent that CH3. Now for the ethyl, notice how there are two carbons. So if I want to depict that as a skeletal structure, I can put 1, 2. So there's just one carbon right here. There's that second carbon right there. And it's implied that there are 2 hydrogens here, and there are 3 hydrogens here, so that both of those carbons can fulfill its octet rule, right? So remember, carbons, they want 4 bonds. And so if all of the bonds between carbons are drawn, everything that is not shown is a hydrogen. And so this is going to represent ethyl. Whereas this is going to represent methyl. Okay. Now I am drawing it with the dots, but that's not how you guys are going to see it. So typically you don't put the dots in. I'm just doing that for clarity. But this is something that you guys are going to see on an exam, problem, lab worksheet, etc., etc. Now, if we have something like this, we have 1, 2, so this is 1, 2, and 3. This is a 3-carbon substituent. And a 3-carbon substituent is going to be named propyl. Okay, so CH2, CH3. So if I include my hydrogens, I have 2 hydrogens here, so that carbon can have 4 bonds. This carbon only has 2 bonds, so it needs 2 more bonds. That's going to be hydrogen. And the last one only has 1 bond, and so therefore it needs 3 hydrogens. So this is CH2, CH2, CH3. Okay. So that's going to be propyl. All right, and so notice how I'm just circling the substituent that contains the vertices. I'm not circling, this whole line that stems into the parent chain. So for example, I'm not circling this portion, I'm only circling this portion because this portion contains my carbon 1, carbon 2, and carbon 3. Okay. This portion is just showing the connection that the carbon is connected to the parent chain. So hopefully that helps lessen the confusion. Okay. All right, so this is the image for the items that we went over. So notice methyl is only depicted by one vertice, 1 dot. Ethyl, there's 2 over here. For propyl, there's 1, 2, 3. 1, 2, 1. Now there is something called isopropyl. And isopropyl is kind of has like this this bunny ears and antenna looking structure. And so, for example, if you guys have something that looks like this, and you have a substituent that looks like this, notice that there's 1, 2, 3 carbons on this substituent, much like how you see it here, 1, 2, 3 carbons. And so it makes sense for it to be prop, because that's representative of 3 carbons, but we're going to tack on this term iso to represent symmetry within that specific group, within that specific substituent. And so isopropyl means that it's symmetrical. It's a symmetrical substituent, but there's still only 3 carbons. Okay. And so once again, butyl, it has 1, 2, 3, 4 carbons. And then this line here just represents the bond, the connection to the parent chain. There's also sec-butyl. And so sec means that it's like attached to the second carbon. And so this is, for example, carbon 1, 2, 3, 4. So notice that the attachment is on the second carbon. So it's called sec-butyl. The reason why it's butyl is because there's 1, 2, 3, 4 carbons on that substituent. And so, for example, okay, we can do, so this is an example of sec-butyl. If this was the parent chain. I need to redraw this in a different color. Just to be consistent. Oops. Okay. There's also something called isobutyl. So once again, it's iso, meaning that there's symmetry. Now, if you guys look at how the attachment is oriented, there are 1, 2, 3, 4 carbons. And so it makes sense for us to use the but. And since there's symmetry, then that's letting us know that we should use the term iso, the prefix iso. And so if you had an organic compound with a parent chain that looks like this, and if you had like isobutyl, then you have something that looks like this. Okay. So once again, there's 1, 2, 3, 4 points on this substituent. And it is very different than butyl and isopropyl. Okay. So just be very, very careful between isobutyl and isopropyl. Last but not least, there's another way to arrange 4 carbons, and that is known as Tert-Butyl. And so, once again, if you count the number of carbons, there's 1, 2, 3, 4 carbons. And the squiggly line is telling us that this substituent is going to be attached to a parent chain. And so if I just drew just like a random parent chain, and if I see, for instance, this cross-looking thing, then I know that the name of this cross-looking thing is going to be Tert-Butyl. Whereas the name of this lopsided bunny ear is going to be Isobutyl. Okay, and if I see a bunny ear that's like standing up properly, then that's isopropyl. but please make sure to count the number of carbons, not my vague descriptions on bunny ears and stuff, bunny ears and crosses. Okay. All right, so those are common organic or carbon-based substituents that's typically seen. And so part of your ability is to recognize what substituent you're working with. And then after that, you guys need to learn how to incorporate the name of these substituents into the parent name of the compound. Okay. Now, for your halogen-based, remember that there were two different types of substituents, carbon-based and halogen-based substituents. So for your halogen or halo groups, so it's a halogen-based substituent. It's nothing complicated like your organic versions. It's just fluorine, chlorine, bromine, and iodine. However, you're going to use fluoro, chloro, bromo, iodo. So don't say, fluorine, chlorine, bromine, iodine, or iodine. It's going to be fluoro, chloro, bromo, or iodo. And so, for example, and we've kind of already seen it in the very beginning of this lecture, you can have like a fluorine here. And so this substituent is going to be a fluoro. Or if you can have like a bromine here, and this substituent is going to be bromo. And as long as you don't pass or break the octet rule, then you can have like a double di-substituted substance on the same carbon. So this is going to be like, I don't know, iodine or iodo. So the key thing here is just to be able to recognize what your substituents are and how is that separate from your parent chain. Okay. Now that we have all of the foundations in place, let's go ahead and start. And so we are going to learn how to name alkanes with substituents. And the very first step, and this is always the first step for a lot of these organic compounds that we're going to learn how to name, is that you need to find the longest continuous carbon chain with an A and E ending. And that's going to be your parent chain. And so in this example that's already been pre-drawn, if you will, notice that the number of carbons in the longest chain is 6. It's not, so when you say 6 carbons, you just need to have 6 consecutive carbons, and that is your parent chain. So your longest chain is known as your parent chain. And anything outside of that parent chain is then going to be your substituent. Now, if you guys see that there's another way to number this, like for example, if this is 1, 2, 3, 4, 5, 6, then this will be your substituent. But notice that they're symmetrical. Whether you choose this or this as your 6th carbon or your substituent, it's you guys are gonna get the same answer in terms of naming the compound. Okay. So that is your first step. And so once you guys have determined your longest chain or your parent chain, you're going to name that parent chain. And so I'm going to name this parent chain hexane because there are 6 carbons and all of the bonds amongst that chain is all single bonds. Okay. So I've identified my parent chain. I've named my parent chain. What's my next step? So my next step is to number the atoms in the carbon chain to give the first substituent the lowest number. So what do I mean here? And so if you look at this image, remember how in the previous lecture or earlier this lecture, I was just like numbering my carbons or numbering my heteroatoms as I see it. I didn't really care. I didn't pay attention to any rules, simply because I'm not naming it. If you're just drawing stuff and trying to translate, trying to make sure that you're not missing a carbon or a hydrogen or a heteroatom, and you're not naming it, you can go ahead and number it however way you want. However, when you're naming organic compounds, you guys have to be precise. You guys have to follow very strict rules. And so this is what makes organic chemistry just a little bit difficult and a little bit tedious, but it's actually kind of like a puzzle. And so after we kind of go through this initial step, I hope you guys can see some joy, if you will, in naming these organic compounds. And so if you guys were to look at this image, I can name this carbon, or I can number this carbon as carbon number 1. And then I can go ahead and number this carbon as carbon number 2. I can number this carbon number 3, 4, 5, 6. Now, that's not the only way to number my carbons. And I can actually do it in reverse. And so I can go ahead and number this carbon as carbon 1, 2, 3, 4, 5, 6. Okay. Or I can go ahead and number this carbon as 1, 2, 3, 4, 5, 6. Okay. Now, since there are 3 different ways of numbering the carbons for this specific example, rule number 2 or step number 2 is telling us that we're going to make sure that we number our carbon chains such that the first substituent gets the lowest number. And so here, the substituent, if we number from left to right, our substituent will be on carbon number 2. And so if you number it from right to left in this example, notice that our substituent is going to be on carbon 5. And so once again, it's still the same substituent. And so since 2 is less than 5, then that tells me that this is the correct numbering of my carbons. And this is the incorrect way of numbering my carbon. It doesn't mean that I always go from right to left or left to right. It's on a per scenario basis. And so you have to judge based on your rules whether or not you guys are going to number left to right or right to left, or up or down up sideways. Who knows? All right, so the next thing that you guys are going to do is you guys are going to name your alkyl groups, your substituents. And so you guys are going to utilize the number 2 to describe the position of where that substituent is attached to the parent chain. And so we have a methyl at carbon number 2. Okay? So remember, meth means 1 carbon. We have a 1 carbon substituent on the second carbon of the parent chain. And so oops. So let's go ahead and just finish this up. And so to name this organic compound, now that we have all of the pieces together, we're going to make sure that we have the parent chain as the last part of their name. So remember that we named our parent chain hexane. And so that means that, so this is going to be the parent. So the parent is always going to be the last item that's named. And anything that goes before the parent is going to be the substituent, typically. And so you guys are going to describe the substituent using a combination of dashes and commas if need be. And so the idea is that the number, instead of putting like a space, so how you guys are going to translate this into like the nomenclature format is that you guys are going to put the number first, and then you're going to put a dash to separate the number from the actual name of the substituent. Okay, so we have a 2-methyl, right? 2-methyl. You guys have to include the dashes or the commas, and we'll talk about the commas in just a second. And so to finish this up, the name, we're going to take this and we're going to put it right here. So 2-methyl hexane. So now that we have the pieces, we're going to put them together, both the substituent and the parent. And so when you guys have, like letters followed by other letters, you don't really need to put commas or dash. And so the answer to this is going to be 2-methyl hexane. So notice that there is no space between the substituent and the parent, since it's all letters. And you'll see in future examples that, in future lectures, that sometimes you will have to add like a dash and a number and all that stuff, just because of how the organic compound is named. Now, this is an example of an organic compound with only one substituent. And so we're going to go ahead and take a look at how to name substituents, learn how to name organic compounds if they have 2 or more substituents. And so the main idea is that every carbon belongs to either the longest chain or the parent chain, or a substituent, but not both. Okay? And so therefore the substituent needs its own number. And if there are 2 or more substituents, If they're identical, we're going to use prefixes to indicate how many there are. So let's go ahead and look at this example. So first and foremost, we need to identify the parent chain. The parent chain has already been boxed for us. And so here we have 1, 2, 3, 4, 5, 6 carbons. And so the parent name is going to be hexane. 6 carbon, hex, single bond, A-N-E. But here we have 2 substituents. And since it's a 1 carbon substituent on both, we're going to say methyl and methyl. And so here, we're going to put in 2-methyl. Okay, so that's where the 2 is going to go here, the methyl goes there. We're going to always separate it by a dash. And this is going to represent 3-methyl. Now what this is telling us is that since they're both methyl groups, then we can just go ahead and combine them into one item. We don't need to list them out separately. And so we're going to use the prefix di to represent that we have 2 methyl groups on this parent chain. And so to name this compound, I'm going to go ahead and say my parent is hexane, and my substituent is going to be 2, 3-dimethyl. And so I kind of jumped like 2 or 3 steps ahead, but let me go back and explain. And so since there are 2 methyl groups, I'm going to erase some stuff here just so it's clear. Okay. So notice that there's a methyl group and a methyl group. Since there are 2 methyl groups, I am going to say dimethyl. Okay. So that's one item that changed. Now, since you guys are describing the methyl groups, but they're at different positions, 2 and 3, we're going to have to use a comma to separate the carbon positions of where that substituent is found. Does that make sense? Okay. And so when we go through more examples, hopefully you guys can understand the pattern. So now that we have the pieces, we're simply going to combine them together, and we'll get 2,3-dimethyl Now, notice that there's this letter is followed by another letter, and so therefore there's no space or dashes or commas. And so it's going to be 2,3-dimethyl hexane. Okay, so hopefully that made sense. All in all, this is the pattern. You guys have your numbers, and then you have your substituent, and then your parent, and the suffix. The suffix can be ane, ene, or yne. We haven't talked about alkenes and alkynes just yet. But right now, the only suffix that you know is alkane, A-N-E. Okay? So as we progress from chapter to chapter, the suffix, your vocabulary for suffixes will grow. Now, if you guys have multiple substituents, you guys need to alphabetize your substituents based on their actual name and not the prefix. And we'll go over examples of what this means. Okay. And you always want to write the number that indicates the location of the substituent before naming it. Hence the reason why the numbers are written before the actual identity of the substituent. And one number must be allocated for each substituent. It doesn't matter if they're on the same carbon or on different carbons. If there are, two or more of the same substituent, then you guys need to, or different substituents, you guys need to provide one number for each substituent. And you're going to always separate the numbers by commas. And then if you have a number and then a letter, you guys separate them using a dash. So number, letter, or letter, number, dash, number and number, comma. Okay. All right, so what we're going to do is work through several examples. And hopefully by the end of this lecture video, you guys will understand how to name alkanes with substituents. Let's go ahead and start. So what is our first step when we try to name alkanes with substituents, or just naming organic compounds? Our first step is always to determine the parent chain. And the parent chain can be found by the longest consecutive carbon chain. And so let's start from here. So that's 1, 2, 3, 4. Okay, that's one possibility. I'm okay with that. But is that the only way to name or to identify the parent chain? Is that the only path? Well, there's another path, 1, 2, 3, 4. And so in both paths that I just took, they both gave me 4 carbons. So right now it looks like, 4 carbons could be it. But there's one more combination that we haven't tried yet, which is 1, 2, 3, 4, 5. Or if we do it in reverse, 1, 2, 3, 4, 5. So 5 is greater than 4. So this is telling us that we have a 5 carbon parent chain. Now, if you guys look at all the bonds within those 5 parent chain, they're all single bonds. And so therefore, it's going to give me that ANE ending. So overall, I will get pentane as my parent name. And so anything that I did not identify as parent is going to be the substituent. And so therefore, this carbon is going to be my substituent. Now, it is a 1 carbon substituent, so therefore it has meth as its prefix. And since it's a substituent, I'm going to use the YL ending. So this is methyl. Now the next thing that you want to ask yourself is, where is this methyl located on the parent chain? And so this is where we have to number the parent chain, number the carbons. Actually, we did a couple steps before this. So number 3, we identified the substituent. Okay, and so it's a 1 carbon substituent, so this is going to be methyl. Next step is to number the carbons on the parent chain. Now I can do this one of 2 ways. I can start from the top, 1, 2, 3, 4, 5. And in a different color, I can start from the right going to the top, 1, 2, 3, 4, 5. So which path, which way of numbering my carbons is correct? And so if you look at the numbers of my substituent, on my substituent, to that of the parent chain, it doesn't matter if I go top and then right, or starting from the right, go to the top. Both of them, both ways of numbering in this scenario, is going to give me an equivalent value for where that methyl group is found, where that substituent is found. And so therefore, I am just going to choose one, because it doesn't really matter. So I'm going to tell myself that this methyl is on the 3rd carbon of the parent chain. And so now that I've identified the parent chain and I've numbered my parent chain and I've identified my substituent, I'm going to simply put all the pieces together. And so remember, the first thing that I need to name is my substituent and then the parent. So the parent is pentane, and the substituent is going to be 3-methyl. So in other words, the methyl group, this guy is in green, is found on the 3rd carbon of the parent chain. Now, put these two together, and your final answer is 3-methyl pentane. Once again, that dash is to separate number from letter. Okay. And yes, you guys do need to make sure you include the little details in your final answer. Okay, so let's go ahead and look at another example. By the way, if you guys can't see it using the skeletal, if you guys can't see it using the expanded structure, you guys can always convert your expanded structure into a skeletal. And so notice how we have 5 carbons on the parent chain. And so therefore we have pentane, so it's 1, 2, 3, 4, 5. And then on the 3rd position, we have a methyl group. Well, 1, 2, 3, that's going to be our methyl group. And that's what the skeletal structure of 3-methylpentane looks like. And you should be able to go from name to skeletal structure and vice versa. All right, so let's look at the next one. So first step, figure out my longest carbon chain, because that's going to be my parent chain. So we have 1, 2, 3, 4. Okay, that's one path. Let's check all the rest. We'll start here, 1, 2, 3. So that can be it. We're already at 4, so that's not right. So we can do 1, 2, 3, 4. Well, still gives me 4. So if I were to do this from left to right, 1, 2, 3, 4, it still gives me 4. So it doesn't matter at this point in time if you try out like other combos. It looks like the largest consecutive carbon chain is going to be 4. So therefore my parent chain is going to be 4 carbons, and they're all single bonds, as you can see. And so therefore my name for the parent chain is going to be butane. So let's talk about the substituent. Now there's a couple ways that we can number this. Zoom in here. I can go 1, 2, 3, 4. Or I can go 1, 2, 3, 4. I don't know if you guys can see that green. So let me just do a different color. 1, 2, 3, 4. Now the substituent is right here. And if you look at the numbering system, it looks like the number in green, number 2 is less than 3. And so our goal is to make sure the carbon number where our substituent is found is the lowest number amongst all types of numbering systems within that compound. So it turns out that if I go from right to left, I'll go ahead and get a carbon number that is less than if I go from left to right. And so I'm going to write that my substituent is on carbon 2 on the parent chain. And since I have a 1 carbon substituent, that's going to give me meth. And since it is a substituent, I'm going to add in YL. And so now that I have all of my pieces, I can go ahead and combine them. So I always want to write my substituent first. So it's going to be 2-methyl. And I'm putting the dash once again to separate the number from the letter. That always needs to happen. Now if it's a letter to another letter, then you guys do not have to do that, and everything is just one word. So the answer to this is 2-methylbutane. So to check your work, you guys can draw the skeletal structure of what you named. So I have butane, that's 1, 2, 3, 4. And then on the second position, I have a methyl group. And so if I were to say that this is position 1, this is position 2, 3, and 4, my methyl group will be right here. And so some of you guys might be like freaking out all of a sudden. It's like, oh wait, no, it's supposed to be on the right-hand side. And so think about what I just drew and think about the three-dimensional character of organic compounds. Okay, and so notice that both of these structures are just flipped versions of each other. So if I were to flip this, it would look exactly like a structure that was given to me. And so it's still an equivalent structure. And that's something that you guys will find when you guys are going from like the actual name to the compound. I personally typically like number from left to right when I'm going from name to compound, just because I read from left to right. And so therefore the compound that I draw will not always be the exact same compound that I see, but it's going to be the same compound if I flip it a certain way. And both answers are still correct. Now if you number from right to left, that's okay as well. Okay. All right. So let's go ahead and check out this example. So we need to find our parent chain. That's the first step. So just by looking at this, it looks like, the longest consecutive chain is along the body of what I'm seeing, like somewhere along the middle. So 1, 2, 3, 4, 5, 6. Okay. Now if I erase this one, if I go down, that's still 6. Now if I back up, and if I go up, that's 5. And so, therefore, that is not the correct parent chain. And the true parent chain is going to be 6. Now, it doesn't matter which one you use, which 6th carbon you use, because you're going to get the same answer. I'm just going to go ahead and use the one that I see, okay, from left to right. And so if I have a 6 carbon parent chain, then that's going to give me hexane. Now I just need to figure out my substituents. Well, it looks like I have 2. I have 1 and I have 2 that I didn't highlight in pink. And so I need to number my parent chain so that I can describe the substituent correctly with the lowest carbon number. So I'm going to go ahead and do this from left to right and right to left. So 1, 2, 3, 4, 5, 6. Now in green, I'm going to go from right to left. 1, 2, 3, 4, 5, 6. Since we have 2 substituents, I need to compare the values for them. So notice that here I have 3 and 4, and here I have 5 and 2. So which of these 2 sets of numbers is the lowest? If you said 2 and 3, that is correct. So 2 and 3 is less than 4 and 5. So that tells me that in this scenario, if I number my carbons from right to left, it will give me the correct numbering system for this organic compound. And so since this methyl group, since this substituent is 1 carbon, it's going to be methyl. And it's on carbon 2, so I'm going to say that's 2 methyl. So here, this other methyl is on carbon 3, so I'll say 3 methyl. 3-methyl. Now, if you guys notice, I have the same substituent. So therefore, I'm going to go ahead and combine them by saying dimethyl, since I have two methyl groups. And when I combine them, I'm going to place the number from lowest to highest. So this is going to be 2 to separate out the numbers. Like, I don't want to put this because that's 23. That's not the same as 2 and 3. Okay. And I can't say this because the dash is specifically for number to letter. So the only way that I can separate them is using a comma. So 2, 3 describes the two carbon positions on the parent chain that has a substituent. And so I'm going to put dash because I'm now going to convert the number into a letter. So the letter is going to be dimethyl. Or the letter is going to be D. So, when you go from number to letter, you have to use a dash. And since I have two methyl groups, I have to say dimethyl. So now that I have both of the pieces that I need, I'm going to start finalizing my answer. My substituent is always written first, so I'm going to say 2, 3 dash dimethyl. And then since I'm going from the letter L to the letter H, everything is just one word, letter to letter, no space. So it's 2,3-dimethylhexane. So this is going to be the name of this organic compound. Okay. So hopefully you guys, it's starting to make sense. Things are like being pieced together. So I just want to work through this example, and I'll continue the rest of the examples in a different video. This video is just getting a little bit long. And so let's go ahead and look at this final structure for simply just naming these organic compounds with an alkyl group substituent. So first step, once again, find the parent chain. And so here I have 1, 2, 3, 4, 5, 6, 7, 8. That's my low-hanging fruit, right? And so looks like 8 is what I get if I go from left to right. But what if I go from this point and branch up? And so let me do 1, 2, 3, 4, 5, 6, 7. Very close, but it's not 8. It's not greater than 8. So far, 8 is the highest. So let's go again. 1, 2, 3, 4, 5, 6, 7. Okay. Still 7, so that can be it. So remember, you're looking for the longest consecutive carbon chain. I didn't do this one yet, so 1, 2, 3, 4, 5, 6. 6 is less than 8, so that's not it. And so you guys can try out a whole bunch of other combinations, but it looks like the highest consecutive or the largest consecutive chain is 8 carbons. And so the name of my parent chain, since we have 8 carbons, is going to be octane. And so everything that I didn't highlight in pink, I'm going to highlight in green so that it represents my substituent. I didn't highlight the other the 3 hydrogens that you guys see, because remember, that's part of the parent chain. That hydrogen is not really an attachment, so to speak. It's part of the parent chain. And so the next thing I need to figure out is the numbering of my parent chain. Okay, so I've identified my parent chain. I've highlighted my substituents. And now I just need to figure out the numbering. And so here in this case, I'm gonna work from left to right and then right to left and see what happens. And so if I say that this is carbon 1, then this is carbon 2, 3, 4, 5, 6, 7, 8. So remember, anything that's in pink that you guys are seeing is my parent chain. So if I go from left to right, it looks like those are going to be my numbers. Now if I go from right to left, I'll have 1, 2, 3, 4, 5, 6, and 7. And so here in this case, we have, 8. So here in this case, we have some differences in numbering for all of these substances, for all of these substituents. So if you look here, I have 6 and 3. If you look here, I have 4 and 5. And then if you look here, I have 2 and 7. And so in this scenario, since we have 3 different substituents, we have, well, technically 2 different substituents, but they're on 3 different positions. What we're going to do is we're going to add up all the numbers and see which one is the least. And that's going to tell me which path to number my parent chain. So what do I mean by that? Well, I have 3 plus 4 plus 7. So that's going to give me 7. I'm sorry, 14. Right? So here I have 3 plus 4 plus 7. That's going to give me 14. And this is going from left to right. Now if I go from right to left, I have 6, 5, and 2. Okay. Or I'm sorry. If I go from left to right, so the green. So if I go from left to right, I'm following the green numbers. And let me switch these two, I apologize. So this is from right to left. Now if I'm going from left to right, notice that I have 2 plus 5 plus 6. So 2 plus 5 plus 6, that's going to give me 7 plus 6, that's going to give me 13. And so notice that if I number my system from left to right, I get a value that's lower than if I were to number from right to left. And so since 13 is the least, then that tells me that I'm going to number my parent chain from left to right. Okay? So hopefully that makes sense. All right, so let's go ahead and put these pieces together. And so if this is my substituent, I have a methyl on carbon 2. And so I'm going to say 2 methyl. Now if you look at this substituent, I have 2 carbons, so 2 carbons means eth or ethyl since it's a substituent, and it's on carbon 5. So I have to say 5-ethyl. So the 5 doesn't mean that you have 5 ethyls, it just means that the ethyl group is on carbon number 5 on the parent chain. And then last but not least, here you have a methyl again, and this time it's on carbon 6. So you're going to say 6-methyl. And so I realize that I have 2 methyl groups, they're the same thing. And so when I write my final answer, I'm going to combine my methyl groups into just one. Okay? And so I'll have like 2,6-dimethyl. Now, there's another problem. When I'm writing my final answer, which substituent do I write first? I have 2 different substituents. I have a methyl and an ethyl. And so, very similar to what the rule said in previous slide, when you guys have 2 or more different substituents, you guys need to organize them by alphabetical order. And so, E comes before M. And so therefore the ethyl should be named first, and then the methyl should be named later. So let's go ahead and put all these pieces together and see what it looks like. And so my parent name is octane. So octane is what I'm going to put at the very end. Now my substituents is ethyl and methyl. Since E comes first before M in methyl, then I'm going to put in 5-ethyl. Now, notice I have 2 methyl groups. So when I combine them together, I need to put 2,6-dimethyl. Notice that D comes before E, but that D and di did not come from the actual name of the substituent. It's a prefix, so you do not count that letter. And so this is going to be dimethyl octane. Okay. And so to finalize my answer, I need to make sure that all my spaces are correct, my commas and my dashes are correct, and all that stuff. And so notice that I'm going from letter to number. That means I need a dash. Here I'm going from letter to letter, so there is no dash, no space, no comma. And thus my final answer is going to be 5-ethyl. It doesn't matter if you lowercase or uppercase or ethyl. So 5-ethyl dash 2,6 dash dimethyl octane. All in one word. So be very careful with how you guys are using your dashes and your commas for more complicated structures. So use the comma to separate out a number if you have 2 or more of those substituents present in your organic compound. And when you go from letter to number, you put a dash. Okay? Letter to number, there's a dash. Letter to number, there's a dash. Number to number, comma. Letter to letter, put them all in one word. Okay. All right, so this is it for this video. I do have a whole bunch of whole bunch of other examples, and I'll go ahead and go through those examples in another video. So that's it for now. Catch you later. Bye.